Okay, just for the record, today we have a seminar on the simulation of atmospheric. I forgot the word. Okay, atmospheric avalanches, electronic and photonic avalanches in thunderstorms by Daria Zemlianskaya. Please continue.
Hello, everybody. My name is Daria. Today I would like to tell you about modeling of interactions in atmospheric physics, thunderstorm reactors, and interaction with hydrometeors. I wanted to start with an introduction. Today there are many mysteries in the physics of atmospheric electricity. One of the key issues is the problem of lightning initiation. Although the dynamics of lightning has been studied in detail, it is not now how the process of developing a lightning discharge begins. To start the formation of lightning, the electrical breakdown is required inside a thundercloud, but the electric fields observed in the atmosphere are an order of magnitude smaller than the breakdown field. Another unexplained phenomenon of atmospheric electricity is gamma ray bursts, which have been observed since 1994 by Space Gamma Ray Observation, created for the registration of gamma rays from space objects. The mysterious nature gamma radiation of the Earth atmosphere is called terrestrial gamma ray flashes. The phenomenon is remarkable for its short duration, on the order of hundreds of microseconds, and high intensity of gamma radiation. Developing a consistent TGF model is one of the key challengers for modern science. Gamma radiation from thunderclouds can be observed not only from space. There are ground-based observatories that register that gamma rays under the clouds. One of them is the Agaraz Research Station, located on the mountain of the same name, is in Armenia. Gamma radiation is not absorbed in the thin layer of air between the cloud and the Earth surface, which has resulted in an extensive set of important experimental data. The phenomenon observed at Agrat station is called thunderstorm ground enhancement. TGE often lasts several minutes, much longer than TGF. So, ionizing cosmic radiation is insufficient for breakdown. Without thunderclouds, there is no TGF and TGE. Thunderclouds are characterized by the presence of electric fields. Consequently, the task is reduced to the study of the electric field, which affects further interactions. Many years of observation of TGF made it possible to establish that apparently this nature phenomenon is based on the acceleration of relativistic electrons in the electric fields of thunderclouds. It turned out that a large-scale electric field can be formed in a thundercloud, accelerating electrons more than they are decelerated when interacted with air. Relativistic electrons are accelerated by an electric field are called runaway. The minimum electric field capable of creating runaway electrons is called the critical field. Runaway electrons interacting with air molecules knock out new electrons, which can also become a runaway. This process leads to the formation of an avalanche of runaway electrons. Seed particles for such avalanches are generated by secondary cosmic rays. Thus, it is possible to consider various mechanisms with avalanches and electric fields that can explain the appearance of gamma ray in the thundercloud. One such approach is the reactor model. The reactor model describes the propagation of an avalanche and the gamma radiation in a thundercloud. Infinite feedback in a cell, that is when the movement of particles in such a cell does not fade, creates an infinite loop that triggers the generation of TGF and communication between the cells in the cloud. Infinite feedback or explosion of the reactor can appear in a system with a large number of separate fields, cells with a uniform field. One such model is the simple reactor model shown in the figure. In the system under consideration, gamma ray will make an overwhelming contribution to the feedback. Let us assume that an avalanche of runaway electrons has appeared in the upper cell. In the course of its development, this avalanche will emit inhibitory gamma, which can reach the second cell. In the second cell, as the gamma radiation propagates, secondary electrons will be generated, which have a chance to turn around and cause secondary avalanches. These avalanches, in turn, emit new gamma rays, thereby closing the process. Theoretical accounting is of such a reactor, taking into account the length of formula wire to increase avalanche runaway electrons presented on the slide. The other parameters assumed constant. To confirm the obtained theoretical ideas, this reactor was modeled in adjunct 4. The model consists of two cells of the same size with an oppositely directed electric field. You can also see the propagation of particles in the reactor.
Sorry, could you a little bit clarify what colors mean on the previous picture? I mean, yellow dots are probably photons.
It's electrons.
Yellow electrons and green are...
On left photos, green. No, on left photos, yellow is electrons.
Electrons being born. It's a point of birth of electron. Yeah.
Mm-hmm.
Okay. So what we do not see is a photon, and on the right, I see green is gamma track. Okay. Thank you very much.
Mm-hmm. A 5 MeV gamma is launched from one side. The air density corresponds to 10 kilometers. We resize the cells and find the explosion. The critical field value was found on the assumption that the ratio of the number of particles through the dividing plane from 1 cell to 2, and from 2 to 1 will approach 1 with time. Thus, we obtained values from modeling that correspond to theoretical concepts, thereby confirming the correctness of the concept. There is also another reactor model, spherical. This reactor accelerates electrons toward the center. They emit gamma rays as they move. They move around the sphere, don't depend on the electric field, therefore they can create a new avalanche, which can create infinity feedback. The considered model has the following assumptions. The main ones are the positive charge is located strictly in the center of the cloud. The critical electric field is the same in the vicinity of the center of a cloud of radius and avalanches of runaway electrons constantly evolve and move along a radius with a constant avalanche rise length. Based on the assumptions, we received theoretical calculations which presented on the slide. They also took into account the Dwyer formula. Reactor modeling. The spherical reactor model consists of a limited spherical electric field. We created a cube in which we set a spherical field. We assumed that in a small vicinity the field does not change. Then at each point of the spherical reactor, the modulus of the electric field does not change. For clarity, the first picture shows a sphere. In the subsequent, once it was removed from uselessness, since the main thing is a spherical field. In the first approximation to measure the required field straight for a certain radius, the particles were launched along the z-axis in the direction of the center. We fixed the value of the field at which the production of new particles did not stop. An endless ground of the generated particles was observed. Since this is subjective, we consider this to be a first approximation. The stimulation also confirms the theoretical results, even in the approximation. Now let's look at particle propagation from the other side. Previous studies have tried to isolate the mechanisms of TGF formation as well as macrophysical characteristics, while the microphysical characteristics of thunderstorm has been ignored. Research shows that the TGF case contains more cloud water, cloud ice, atmospheric precipitation, and atmospheric ice at high altitudes compared to storm without TGF. It also turned out that it is quite difficult to interpret the data from the tropical rainfall measures satellite, because the density of clouds, that is the number of hydrometeors there, varies by orders of magnitude. Thus, there is interest in considering the influence of hydrometeors in a cloud. This task can be approached from modeling. We created a rectangular parallelepiped with a length of 600 meters along the z-axis. The volume contained 10 to the 10 power ice. The electric field is directed in the opposite direction of electron propagation. The electron unfolds under the action of the field. The model showed the following result. The number of electrons increased in comparison with the model without ice flows by 7.8%. The energy of electrons also increased. This model also shows that the coordinate distribution of the produced particles has not changed. As for me, that's all. That is all. Thank you for your attention. Have you any questions?
Okay, very nice report. It's a really, really nice report, and I think it's your bachelor thesis made for you right now. You can do it a year ahead of time. Of course, the only problem I see right now is that I do not see the conclusion slide. You usually want to include conclusions in this kind of talk, because people tend to see them. Please do it the next time. Okay, personally, I have only one question, and say for the one when will be the paper ready? Because it's definitely a material for a good paper. How much time does it take to make one simulation in 2-cell or spherical cell simulation in Giant on the remote computer?
How I cannot? Can I?
Oh, yeah. That's a question.
No, I modeling for spherical and simple reactor on Giant. And
does it take several minutes or several hours or several days to complete the simulation?
I think maybe simple reactor. It's 1 week maybe, but with some
modifications.
Yes.
And you are always taking about how many particles? 10 to the 10th? It's a standard number, or you have a different numbers of particles simulated?
It's different particle. I will simulating with another number of particles, and I will calculations some function that's described.
You can answer in Russian if you want. That's okay. It's internal seminar after all.
Ну, в будущем я хочу, я сейчас занимаюсь тем, чтобы посмотреть на различные, на зависимость от количества, как будет влиять количество гидрометеоров в данной ячейке на то, как оно влияет на опять увеличение электронов в этой ячейке.
Dependency of enhancement factor on the hydrometeor amount. Okay, are there any other questions?
I have a simple question from general physics. Okay, let we have a cell filled with air, and then we have some electric field, and then we have some number of particles after relativistic runaway electron formation within a cell without hydrometeors. So just simple cell. Then we add hydrometeors, and we see the same air density, but apart from this air density, we have hydrometeors, which is also some kind of friction acting on relativistic runaway electron avalanches dynamics. Why do we have increase in number of particles and just decline? Why number of particles increases with hydrometeors, but not declines?
We have increased a number of electrons when we increased ice particle, and electrons.
I think that it's a simple cross-section of electron production is higher in hydrometeors. By the way, I just have a thought that it is possible that in this medium, I mean, including the hydrometeors, the Dwyer model could actually work better.
Yes, if we have increase in relativistic runaway electron avalanches, folding factor, yes, and we.
No, I mean that one of the main problems why the Dwyer model does not work in normal conditions is that those positrons go far away from the cell and then interact. So if you add some kind of friction inside your medium, it is possible.
Then we have much higher number of
yes.
positrons.
So the number of escaped positrons is lower. So the feasibility of Dwyer's model is higher.
Well, it's a really good thought. We will work on it because, yes, it's a great idea. Higher frictions and higher number of positrons, it might work out.
I'm not sure because in higher friction you will higher energy losses, and this means lower.
According to Daria's simulations, we have increase in number of particles. Consequently, as far as I understand, we have increase in number of relativistic runaway electrons.
Because gamma does not escape, less escape factor, smaller escape factor.
Okay. Maybe.
Other questions? Or okay, no questions. Again, Daria, it's a great presentation. I mean, for second year, third year, I'm not sure. So keep up. Now the third, yes. Keep up the good work, and your English was quite well as well.
Thank you.
Let me stop the recording.